And welcome back for another video. So in this video, we are discussing the Hvorslev method. So we're still in those slug test graphic methods or slug test, type curve methods for finding aquifer properties from bail down or slug test data. So this method is a little different from the previous one. It has the upside that you can typically do this in unconfined and also in wells that are not completely penetrating. So you don't really need to know the depth of your aquifer to use this method. So this is very convenient. Now the downside, obviously, if you don't know what if it's not a fully penetrating well, you cannot find the transmissivity, obviously, because you don't know, the depth of the aquifer. So the only thing you can find from the Hvorslev method is the hydraulic conductivity of, of the space around the well, basically. So it's also not, it's not integrating through the whole aquifer. So basically, when you do those kinds of, it's like a local test. Basically, you're just, evaluating the hydraulic conductivity of the material right around that piezometer that you're using for this, right? So it's not like, the whole aquifer, basically. Okay, so typically you want wells that are, LC over R greater than 8, meaning the length of the casing, right, is much longer than the radius, which, usually is going to be true, but that's something to keep in mind. And here the whole method relies on T37, right? And what is that? Well, this is very simple. This is basically the time it took for the head to recover to 37%, right? So again, look at this y-axis here. So if we start at 1, so again, this is a ratio of head, right? So we start, at the beginning of the test, you're the highest, the head is the high, or the water in the well is the highest because you just, raised it with the slug. So this is 1, right? And then it goes down, 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 and this is what this y-axis is here. And now you wait for it until it's at 37%, right? So it dropped 66%, if you will, but until you get to 37%. So literally what you do is, catch this number, draw the line, and then go read the time. So that's what T37 is the time, right? The time it took to reach that 37% of the initial level. Okay, so here in this case, that would be like 4 seconds, right? So T37 is 4 seconds. Now that's all you need. Everything else you should have, right? Everything else because R obviously is just the radius of the well casing. Big R is the radius of the screen. Again, screen and casing, they may or may not be the same. LE is the length of the screen, and that's it. So really all you need to do is read that T37, plug it in, and you're done. Here in all the parameters are given. If you plug everything in, you should find that the hydraulic conductivity is about 9.78 10 to the minus 4 meters per second, and if you convert that in meters per day, you find that it's almost 85 meters per day, which is quite a lot. So that's a very permeable media that you have in that well. This is just another example where, just to show you that oftentimes, those data, like I mentioned before, typically at the very early times, you have that skin effect of, either a gravel pack or, maybe there's some fines that came into that gravel and kind of plugging that screen a little bit. So again, typically very early on, what you're measuring is, some skin effects basically you don't want. So make sure that when you do take those fittings, right, you wait for that sort of linear range, again, semi-linear, right, because this is actually a log on the y-axis here, but exponentially linear, however you want to call it, but that sort of stable behavior range to find that data. If you don't, that's a problem. Here, your T37 is right there, and that would be 30 seconds in this case, right? That's just another data set. Another thing to keep in mind, if you have a conducive media or something that is easy to rush water into your well, the problem is it might recover very fast. If that's the case, obviously you can't just measure it every few seconds, because it might take only a few seconds basically to recover. So in those cases, you'd need a transducer or some kind of electronic method of measuring that drop. That's very fast. Obviously, you can't just do it by hand. Another example from the book, from Fetter. This is all in Fetter, chapter 5, towards the end of chapter 5. And again, just the T37 is right here, right? And this is an example where that's like 1.8 seconds, let's say. So obviously this data, you would need some transducer to measure, basically. So this is the data, this is the data that's plotted on the right-hand side here. This is the parameters that are given to you, and again, you can just plug them in and find the hydraulic conductivity right around that hole. Okay, that's it for this lecture. There is one more method that we'll see in the next video. Thank you.